of a completely continuous operator by finite rank operators, and that approximation is in the norm. That is, if Tn is the sequence of operator, norm of Tn minus T tends to 0, right? So let us recount. We had an operator T which had an infinite dimensional domain and infinite dimensional range. By passing on to the operator Tn, what have we done? We have kept the infinite dimensional domain as it is, but the range has been made finite dimensional. But then this means we have to be satisfied with an approximate solution of our problems and so on. Anyway, so the range is now made finite dimensional, and we saw how can it be done in many, many situations that we encountered. Now our next job is to cut down the domain from infinite dimension to finite dimension. And this has been classically done in many, many ways by what they call discretizing an operator. Unfortunately, every discretization procedure had its own methodology, had its own way of going about things. Let it be a projection method, let it be degenerate kernel method, or the Nystrom method, or the natural method that I told towards the end of the lecture. There were many, many different ways. And depending on the way, you have to discretize and then reduce it to a matrix situation. Sometime in 1986, an American mathematician, Robert Whitley, suggested that all these methods of finite rank approximation can be unified into a single procedure. And later on, about 4 years later, Lalita Deshpande, a former student of mine, and myself, we carried forward that suggestion, and we have accomplished it. So I'm going to present that to you today. What it does is, no matter what the discretization procedure is, no matter what method you are using to discretize, there is a definite particular way of constructing a matrix corresponding to that discretized version, and you solve the linear equations, system of linear equations corresponding to that matrix, or the eigenvalue problem for that matrix, and be done with it. Then you get the solutions of whatever discretization approximation you had used. Of course, that matrix is not the same for all methods. That will be silly. But the way to construct the matrix is absolutely the same. And so you can write down one algorithm. And in the algorithm, whatever are the particular situations as far as construction of that matrix goes, you put in those numbers, finish, and then solve the matrix eigenvalue problem or the by using Gauss elimination. So that is what I want to show you today. So in all this, if you have a finite rank linear map, by the way, from now onwards, we will not talk about continuity, etc. Nothing. Now it is absolutely simple first year linear algebra. There is no linear analysis. Just we talk about linear equations and matrices and so on. Okay. So the most important observation is that by the way, so first of all, let me go back. I suppose everyone knows what a linear functional is. A linear operator on X is a map from X to X. A linear functional is a linear map from X to the scalars. Scalars are the complex numbers. So a linear functional we denote it by small f. It is a linear map from the linear space X. Now look here, I'm not talking about Banach space. Forget about all that. Completeness, nothing is needed now. It's a linear space and a linear map from the space to complex numbers. So you know what that is. So our most important observation is the following. If you have X a linear space and capital F is a finite rank operator, what does that mean? Capital F is a map from x to x and it is linear. And the range of the map is finite dimensional. That's what it is. So a map F is a finite rank operator if and only if the following holds. What is it supposed to hold? There should be some fixed number of vectors in X, that is fixed number of elements in X, and a fixed number of functionals on X, such that f at X should be obtained by f1 at X times x1. X1 is a vector, remember. F1 at X is a complex number, plus so and so on. Fm at X, it is a complex number. The value of the mth functional at that particular X times x at m. X at m is the element of X. So a finite rank operator, nothing about continuity, nothing, just a finite rank linear map. F is such a map if and only if F can be presented in this manner. Okay, now it is almost trivial to prove this, but I shall take a few minutes to show this. First of all, if F is presented in this like this, is F linear? Surely. X is a fixed, x1 is a fixed vector, xm is a fixed vector, f1x is linear, f1 is linear. So the first component, first coefficient is linear map. The mth coefficient is also linear. So f1, f2, fm are linear, and you are taking a linear combination of these. So therefore, capital F is a linear. So one way is finished. The other way, given a finite rank operator, how to obtain x1, x2, xm, and how to obtain the functionals f1, f2, fm, so that fx is equal to this. Now, this is also very simple. I have written the proof, but let's go, because otherwise we'll spend the time twice. So suppose now that F is a operator of finite rank. Take x1, x2, xm to a basis of the range. What do we know about F? It is a finite rank operator. That means the range is finite dimensional. So it has a basis, finite basis. So take a basis. What does basis mean? Every element of the range can be written as a unique linear combination of x1, x2, xm. So write it. So for every x, there are complex numbers C1x, CMX, such that the image F1x, it is in the range, right? It is a linear combination of the basis elements. That's what I've written. Finished. You got what you wanted. X1, x2, xm are these basis elements, and C1x is the first functional, is it not? The coefficient of a basis is a linear functional. So F C1x, you call it F1x. CMX, you call it FMX. So this is a very trivial observation, but it is the most important observation. Why so? Because when I write the way the proposition here, F is a finite rank operator if and only if there are such elements, m elements in X and m functionals on X, such that F is in this statement. I have not used bases, nothing, just m elements and m functionals. The basis, etc., used to give you an example how to construct F, but you don't have to do that. And I say that most finite rank maps that we have come across so far, you don't have to worry about what to take for x1, what to take for xm, what functional to take. You stare at it about 2 minutes and you know what are the elements x1, x2, xm you should look at, and what are the functionals f1, f2, fm you should learn. And I'm going to give you examples. I hope you don't get bored with the examples, but for me, unless there are many, many examples, all this theory makes no sense unless it can be illustrated in many, many examples. So I'm going to give you examples where all the finite rank approximations that we studied in the third lecture, how they can be presented in this particular form. Now you may ask, why are you worried about this particular form? Because this is the form which will allow me to construct a matrix corresponding to the finite rank approximation Tn. So I'm going to come down to that particular matrix using this particular presentation. So first I will show you. So as I told earlier, forget about continuity, forget about Banach, everything is, you can forget. There is no analysis now. It is only linear algebra. All right. So that is what I want to show, that given a finite rank linear map F, how to find out these elements x1, x2, xm and the functionals f1, f2, fm, so that you can write fx like this. And this I will do by giving you many examples. Mind well, there is no linear independence needed here. You don't have to worry about linear independence. They don't have to be basis elements, nothing. Just there should be elements. Okay, so here are many examples. So now I think in the last lecture we spent enough time on looking at these examples and telling you what are the matrix representations and so on. So I think I will go a little quickly because this is the last lecture and I cannot say I will do it in the next lecture. So we'll quickly finish, and you'll have all the notes with you. So even if you don't go as fast as I'm going in your mind, you can look at it a little later. All right, so we'll go through the same examples. I'm not taking any new examples. So you are familiar with all these examples. I just want to show how they can be put in this framework. All right, so what is the first example? X is L2, little L2, square semabel. L is a linear map on X. Now earlier we talked about T is a linear map. We talked about T being completely continuous, etc., etc. Forget it. It's just a linear map. So Tx is given by Tx1, Tx2, and so on. Is it not? First row multiplied by the vector x, second row multiplied by the vector x, and so on. So this is my basic vector, x at 1, x at 2, etc. Then we looked at the projection pi n, which was the projection truncate the vector at the nth stage. So keep first entry, second entry, nth entry as they are, put all later entries equal to 0. So with this pi n, we wrote down a projection operator Tn of p. What is Tnp? It is pi n composed with Tx. So let us do that. This is Tx, right? Pi n of Tx means what? Keep the first n entries as they are, which I have done here, Tx1, Tx2, Txn, put all the entries equal to 0. So you have a vector which has only n non-zero components. So can it not be expressed in terms of the first n standard basic vectors? X1 should be what we usually call E1, that is 1, 0, 0, 0. X2 should be E2. So here I'm writing Xj should be 0, 0, 0, 1 in the jth place, and 0. So this will be accounted for by X1. The last one will be accounted for Xm. And what about the functional? This Tx at j, is it not? This is the entry. So this entry times 1. So this 1 comes from here, X1, finished. So Tmx is presented in the form that we want in a very simple and very straightforward way. You look at what the operator is doing and it is obvious to you what you should do. There are only n non-zero components. So you take the first standard basis vectors, E1, E2, En, or whatever we call X1, X2. All right. So example 1 is done. Example 2. Example 2, the operator Tx was just looking at the Fourier series of X. Okay, this is the Fourier series that is represent Tx as the Fourier series of Tx. These are the Fourier coefficients here. Okay, so we want to represent it in the standard form that we want. So what is the projection we looked at? Let me go back. What is the projection we looked at? The projection pi n was look at X, look at its Fourier series, truncate the Fourier series at the nth stage on both sides, plus n minus n. So this was the projection. Do you recall? Just about 1 hour ago we studied this. Pi nx is the truncation of the Fourier series at the nth stage. This is the jth Fourier coefficient. So this is pi n. So let's look at Tnp. What is Tnp? Pi n of Tx. That means you look at the Fourier series, Fourier coefficients of Tx, and look at only the first n Fourier coefficients on the left and on the right. So it's clear now. What should be the basis vectors? Now the basis vectors, how many will be there? They go from -n to +n. So how many are there? N on the positive side, n on the negative side, and 0. So there are 2n plus 1 vectors. That's why when I wrote down the general result, I used the index m. M can be equal to n, m can be equal to 2n plus 1, depending on the situation you are approximating. So because the Fourier series, I'm writing the complex form of the Fourier series, therefore it has plus and minus Fourier coefficients. So the xm, the jth element is e to the power ijs, because that is what appears here. So you look at it and it's obvious to you. And what will be the functional? This is the functional. The coefficient is the functional. So fj at x at cj at tx. So as I said, if you look at, write down the approximating operator and just look at it 2 minutes, very carefully look at it, it's obvious to you. You don't have to make any work, you don't have to do any work or scratch your head, oh, what should I take for functionals? What should I take for vectors? It's looking at you. If you don't look at it, it will look at you. So it's obvious. Okay. Then we look at the interpolatory projections. Remember, when you have continuous functions, you interpolate the continuous function by a piecewise linear map with the help of hat functions. So pi n x. So let us see what happens here. So what is T and P? Pi n of Tx. What does that mean? Evaluate Tx at the node and then use the hat functions. These are the hat functions, E and J. Is it clear what functionals to be taken, what vectors to be taken? Obviously, these are hat functions are the functions. So xj equal to the jth hat function corresponding to the node T and J. This is the node T and J. How many nodes are there? We took here n nodes. You can take whatever number of nodes you want, depending on how close an approximation you want. But this is standard. Take the node at 1 by n, 2 by n, 3 by n by n. So n nodes. So the jth element of the linear space is the jth hat function. And what is the functional? The functional is the, the function Tx evaluated at Tjn. This is not, T is a map from C01, that is set of continuous functions on 01, to set of continuous functions on 01. So T of x is a continuous function. Evaluate it at the nth node. So again, the choice of the functionals and the choice of the elements of the vector space is obvious. It is here. You don't have to look for anywhere else. So this is as far as the projection approximation is concerned. Now, remember, I also told you a slightly more involved approximation, a modified projection approximation. So that I have not written down here. This I will give you as an exercise. And if you can do this exercise, then you will be sure that you have very easily understood whatever I have talked so far. So the 3 examples, 1, 2, 3 that I just gave above, you work it out for T and K. That is a modified projection introduced by Rekha Kulkarni that I told you in the last lecture. So the first part of that is what we already done. The second part is pi n is on the right side. This is the approximation due to an Australian mathematician, Sloan, and pi n is the Galerkin approximation. And this particular combination was considered by Rekha Kulkarni, and it has proved to be very, very efficient in approximation. So I suggest that you do this exercise. Fine. Now let us come to the second method. The first method was projection method. The second method is degenerate kernel method. What does it do? Given a kernel K of an integral operator, you look for degenerate kernels. What does that mean? A degenerate kernel means it's a function of S into a function of T. A function of S into a function of T and the summation. So you have to look at the degenerate kernel operator. And this is the degenerate kernel operator. So you integrate the kernel here. When you integrate the kernel, you are integrating with respect to t. So x and js has nothing to do with t, so it comes out. And you integrate this one. So t and x at s for a degenerate kernel is already presented like you want. So what are the elements of the basic space that you are looking for? These are the elements, x and j, the first factors. And what are the functionals? Integrals with the second factor. That's it. So there is nothing more to do. So this is equal to f1x, x1, fnx, xs, where the elements are these first factors and the functionals are integrals of the second factors. Okay, so as I wanted to tell you that it's very easy to look for functionals and the elements of the Banach space, which will give you that particular form. Okay, now I suppose this is the last example. This is the example concerning the natural approximation, or N can stand for Nystrom approximation also. What does it do? Nystrom approximation, it takes a continuous function x, it evaluates at the nodes, right? And for the, this is an approximation of the integral operator with kernel ks, kernel. So what does it do? Evaluates the kernel at the evaluates the kernel in the second variable of the kernel at the node and keeps the first variable as it is. So TNS, this is the definition, right? We talked about it towards the end of the last lecture. So what are the functions and what are the functionals? Very easy, because I want to write it in this form. So WNJKS, this is the first element or the jth element, and f at xj is tx evaluated t and j. Fj at x is x evaluated t and j. So in all the examples that we have seen so far, it is absolutely easy to put a approximating operator of finite rank in a particular form. What is the form? This is the form f1, a functional evaluated at x, times a vector x1, fn evaluate x at mth functional times a vector xn. Now, as you can see in the 5 examples, there were different functionals and different elements or different vectors. It depends on what approximation you are looking at. In most approximation, it is obvious what you should choose. Okay. So now comes the big proposition. This is the big proposition. What does big mean? Big means it takes care of all possible finite rank approximations. The moment you have a finite rank approximation, it will be of this form, f1x equal to f1x. I gave you 5 examples. You bring any other example to me, I will show you how to put it in this form. The moment you have put it in this form, right, the problem of solving an operator equation involving the finite rank operator capital F. Remember, each Tn, an approximating operator for T, has 2 properties. What are the properties? It is linear and it is finite rank. Is it not? That's what we concentrated on. So each Tn is of the type F. F is a linear operator and it has finite rank. That's all. Nothing about continuity, nothing. So every Tn can be put it into this form. So if I tell you how to solve operator equations or eigenvalue problems for a linear operator of finite rank given in this particular formulation, then you can do it for Tn. It's simply, you have to decide what is x1, what is x2, what is xm. You have to decide what is f1, what is f2, what is fm. And in the 5 examples, I showed you that it's obvious what is to choose. Okay. So here is a proposition which takes care of all such finite rank approximations. Okay. They are linear and they are finite rank. That's all that we want from it. Okay. Now I will, the statement of the proposition is little long, but I want to show that statement to you. I want to comment on the statement and I want to comment on something much more deeper than just the statement, and then we shall see whether to prove it or not to prove it. Okay, so given a finite rank operator of this form, I form a matrix. So this capital F, what are the attributes of this capital F? Capital F is defined on an infinite dimensional space X. X is a linear space. It can be infinite dimensional. But its range is finite. The range of capital F is finite dimensional. Using that and you looking at the exact formulation of that F, we have written down this particular presentation. So given F, I will form a matrix A. This is the most crucial part. How to form the matrix? Evaluate the ith functional on the jth element. How many functionals you have? F1, F2, Fm, correct? How many elements you have? X1, X2, Xm. So the ijth element of A, is it not? Ijth element means what? Element in the ith row and the jth column. So to tell you what the matrix is, I have to tell you what is the element in the ith row and the jth column for I and j going from 1 to m, right? So what is that element? Look at the mth function, ith functional, and evaluate at the jth vector. Okay, so is it easy to form the matrix A? Yes. Just look at the functionals, look at the vectors, evaluate the functionals at those vectors and put them in the appropriate place. Ith functional evaluated at the jth vector is the ijth element. All right. So far no problem. Given a finite rank operator F, you can form the matrix A. My claim is that whatever you want to do for the finite rank operator, you need to do only for the matrix A. You forget everything else. Everything else you forget about the finite rank operator, including its domain, forget it. Just concentrate on this matrix A. And this matrix A will give you everything you want. And that is the statement of the proposition. So I want to show you that statement. I want to comment on the statement, and then let us decide whether to prove it or not to prove it. Okay, so here is the statement. What is the data? The data is a non-zero complex number C. What is this complex number Z doing here? Remember, it is with us from the very first lecture. Starting with a complex number Z, we started wondering whether it is an eigenvalue or not. If it is not an eigenvalue, then the operator equation ZU minus AU equal to V has a unique solution for every V. Remember that? If Z is a eigenvalue, then we said ZU minus AU equal to 0 has a non-zero solution. That was case 1, case 2. And similarly, we built up case 1 and case 2 for the infinite dimensional situation also. It is that same number Z. So you fix a non-zero scalar Z. And we want to now solve the operator equation and the eigenvalue problem for the finite rank operator F. And I say it is enough to solve the corresponding problem for the matrix A. Why do I say that? And I will tell you why it is so. So Y is a fixed element of the linear space X. It can be infinite dimensional. In general, it is. But from Y, only I find the M attributes of Y. What are the M attributes of Y? The first functional here, F1, evaluate that functional at Y. Second functional, evaluate at Y. Mth functional, evaluate at Y. So you get a M-dimensional column vector, right? The super T means it's a column vector. So V is the column vector formed with the help of the right-hand side Y of the operator equation. Okay, V is just the vector Y. So I don't care what Y does elsewhere. I want to know what the value of Y, what the value F1, F2, Fm give to Y. All right. So this is the data. Y, Z is the fixed complex number. Y is the given vector or given element of X, from which I create this vector V. And here is the statement I want to tell you. Now, I will read it with you, and I will again and again read it with you to emphasize what it involves and what it does. So let us first read it very simply, and then I shall come back and read it again and again with you. Then the statement says, for a element X in the linear space X, infinite dimensional, and a vector U, U1, U2, UM, it's a m-dimensional column vector, right? These two equations are valid if and only if these two equations are valid. So let us look at what these equations are. The first equation is in the big space, zx minus fx equal to y. This is the equation we want to solve, is it not? This f is going to be Tn, the nth finite rank approximation of T. So this f really is representing the nth finite rank approximation. But let it go at the moment. So this is an operator equation in the big space, that is Banach space or whatever you have, infinite dimensional space. What is this U? U is whatever is the solution of, we don't know what that solution is, but whatever X satisfies this equation, evaluate the functionals F1, F2, Fm at that X. So you create this vector U. So this equation is satisfied by X. And if you write down U in terms of X in this manner, then what happens? This particular U which you have created using this solution X will satisfy this matrix equation. What is the matrix equation? A ZU minus AU equal to V. What is V? We know. Given Y, we have created a V. Understand? So if the original solution is satisfied by X and you create U using that X, then that U will satisfy the linear system, M cross M linear system. Okay, M equations in M unknowns. And this X, which is the solution of the operator equation, can be recovered in terms of U, this U. How do you recover it? 1 upon Z, Z is given, Y is given, and U is available. U as the solution of this equation. So U is available. So X, which was the solution of the operator equation, can be recovered from this U. What is this U? It is defined in terms of X. Okay, so this is one part. That is, if these two things are given, the top two things, then the bottom two things are available. But that is not what we want. To do this, we should know the solution X. No, we don't know the solution. That is the whole problem. So we really want to go backwards. That is, if we know U, which solves this system of equations, and if we define X in terms of U in this manner, then this X will solve our equation. Understand? And that U, which was our solution to start with, will be recovered from this X in this manner. I hope I have said enough about these two equations on the top and these two equations in the bottom. I will repeat it in some other manner. The top two equations say that if you know a solution of the operator equation and you create a vector using that solution, then you have a solution of the linear system. And that given solution of the operator equation can be recovered from this U in this manner. Conversely, if you simply solve the finite rank, the finite linear system, M by M linear system, and write down an X in the big space. Big space means infinite dimensional space. How do you write it? Write it 1 by Z. Y is given to you. It is the right hand side. This is the right hand side. Plus U is available to you from here. And what are x1, x2, xj? These are the elements of the finite rank operators. If you write x like this, it will solve the equation you want to solve. So really speaking, in our practice, we want to go from the last two equations to the top two equations. And when you do that, the solution that you had here is related to the solution x in this manner. Okay. Now you may say that why did you write if and only if? You only want to go from the last to the first two. Why did you want to write if and only if? There is a reason. When you write if and only if, it means that this is the best you can do. You cannot do anything better than that. So that is one reason. But there is one more reason. One more reason is going from down to up gives you one way of solving. But you may say to yourself, oh, there may be some other solutions also. Who knows? There is only exactly one solution. We have not said anything about eigenvalue being 1-to-1. Nothing we have said, no? Being on to, nothing we have said. So you may say solving the bottom two equations will give you a solution that you want. But that may not be the only solution. There may be many other solutions. To that, I will say, whatever be the solution you will find, it has to be obtained in this manner, because you go from top to bottom. Do you appreciate me? This if and only if statement has the advantage of not only showing you how to find a solution, but also of telling you this is the only way you can get solutions. There are no other solutions. Okay, so this is a beautiful result in my mind, because it does exactly what it wants, what we want it to do. It gives you a solution and it says these are the only solutions. Now, of course, you will say that, oh, it's a good result. What about the proof? Is it very easy? My answer to this, I want to spend maybe 2 or 4 or 5 minutes on answering this question, because when we in mathematics we first of all define things, right? This is definition by definition, this that. Then we say, oh, using these definitions we shall make a statement. Okay, and then we shall give a proof. Students find the proofs to be the most difficult to deal with. Do you agree with me? I can't see your faces, but I know that all students find, oh, let's leave the proof. It's pretty difficult. Let's not do that. Tell me what the definition is. Tell me what the statement is. I will try to use that statement. I don't want to know the proof. It must be very complicated. This is very unfortunate, because I have heard what I'm going to tell you now. I have heard it from very top mathematicians. In particular, you may have heard about Rota. Is one of the finest mathematician of the last century. What he says, I will tell you what Rota says. The most important thing in mathematics is to make the correct definition. If your definition itself is not to the point, you cannot hope to prove, or you cannot hope to get nice results. So the most important thing is to define the correct way. That is, whatever you want to analyze the situation, this is the crucial part. So the term you define must be the crucial term which is going to throw light on the rest of the procedure. So the most difficult thing in mathematics is to define the right kind of things. The second important thing in mathematics is to formulate the result in the nicest possible way, using the definition you have made. For example, we know here here the definitions are really trivial. There are no great things we have defined. We have talked about what is meant by a linear space and what is meant by a finite rank and so on. So these are standard and well-known and very precise definitions. But if you look at the formulation of the result, right, the result is so correctly and pithily formulated in a situation where the definitions are correct and the results are correctly formulated, the proof must be trivial. So we should never be afraid of the proof. The proof has to follow. I'm not saying trivial means can be given in one line. That is not trivial. What is trivial? Trivial means, I will tell you, given this, you want to prove this, right? So that means you know you, right? Substitute here, you know A, you know V, substitute here, see whether the equation holds, right? X is given here. How do you prove it? Divide throughout by Z, you get X. Look here. Divide throughout by Z. What will you get? X. And put FZ on the other side. So X equal to 1 by Z. Y is already here. F of X. This is F of X, is it not? Because F of X is F1X, but here F1X is U1. So is it obvious that these two things are given? Then the second part will automatically be available? Yes, it is follows from the definition. What you have to do is, given this and given you, whether this equation is satisfied. Well, you know the solution, you know the equation, substitute and find out, and it works. That is what I mean by trivial. Trivial means there is no trick. There is no work involved. Shall I go this way? Shall I go that way? Nothing. It's clear. If X is the solution of this and U is given in terms of X, substitute for U. You already know what is U, right? I hope you know what is U. Anyway, so given U, substitute and you will find it is satisfied. Well, if I have written it correctly, it should be satisfied. If it is not satisfying, then I have made some statement wrong. Okay, so that's why I think there is no need to prove. There is a proof that I have written, it runs 2 pages. But I think there is absolutely no reason to go through the proof because it's a substitution. And you are not in the first year of college or second year of college where you don't know what to substitute where. You have done substitutions so many times, is it not? Our initial mathematical work is all full of substitution. There is a method of substitution also, no? In integration and so on. We know all that. So it is a method, just you have to substitute. How about going backwards? Suppose you know what is U. Okay, then I'm telling you, define X in terms of U like this. Then I have to substitute X here and get Y. Will you get Y? Yes, I'm saying you will get Y because I have written it correctly. So my point is that defining things is the most important thing. Formulating the result is the next important thing. If you do correctly, then the proof should be straightforward. Let me not say trivial. Trivial would mean that, oh, you can do it in one line. No, that's not what I mean. The proof has to be straightforward. There is no energy lost in thinking about, should I go this way? Should I go by reductio ad absurdum? That means suppose not. Should I do that? Nothing like that. Simply substitute. Okay. So with these comments, I take your leave from proving this result. So I'm not going to prove the result. I will show you. I have written it here. You can substitute and verify that it works. I'm not saying it is a one-line proof. Huh? It is a proof by substitution, and it takes a little bit of time. So I say that you spend some time, those of you are, so this is one part is over in one page. Second part, it will take the second page, and then the proof is over. Okay. So now let me recount what we have done. We wanted to solve operator equations and eigenvalue problems corresponding to a finite rank operator. What we have done, with the help of the finite rank operator, we have created a matrix. We have told you an algorithm for creating a matrix. And we say, do what you wanted to do for a finite rank operator defined on an infinite dimensional space. Do it only for that matrix. Then you will get what you want. Okay, this is the moral of the story. So I have done it for the operator equations. Now it's a simple matter to do it for eigenvalues. Usually, eigenvalue problems are much more difficult to prove and solve and so on. But in this case, the eigenvalue situation follows immediately. this is what I have written again. If you want to solve the operator equation zx minus fx equal to y, remember f is what we were having already as Tn, the finite rank approximation. If you want to solve and z is not equal to 0, then solve this matrix equation and then x will be the solution. X is obtained in terms of the solution of the matrix. And more importantly, further, all solutions of the operator equation are obtained in this manner. Why can I say this? Because I can go backwards. I can go forwards, I can go backwards. That is why this is the only way to find solution. Okay, now I have said enough about the methodology. Now let me tell you about the eigenvalues. So suppose lambda is a non-zero complex number. Then if f is a finite rank operator on a linear space presented as above, in the same way that we have been looking at, then lambda is an eigenvalue of f if and only if lambda is an eigenvalue of A. That means the eigenvalue problem for a finite rank operator can be solved by solving a matrix eigenvalue problem. Not just the eigenvalue, but you can find the eigenvector. So, phi will be an eigenvector of f if and only if u is an eigenvector of A, and using u, you can define phi in this manner. That means to solve the entire eigenvalue problem means to find an eigenvalue and to find all possible eigenvectors. Remember, there can be many eigenvectors. The eigenspace can have many dimensions. Okay, so all those eigenvectors will be found by solving the eigenvalue problem for the matrix A. What is the proof of the corollary? Extremely simple, because we have already talked about the equation ZU minus AU equal to V, right? To consider the eigen equation, what you have to take the right hand side to be equal to 0. If the right hand side is equal to 0, we define in terms of the element y by evaluating the functionals on y. But y is 0. F1, F2, Fm are linear functionals. So this is equal to 0. So it's the 0 vector. Okay. So instead of z, writing lambda, and instead of x, I'm writing phi. So exactly the two statements at the top will say lambda phi minus f phi equal to 0, and u defined in terms of this phi if and only if lambda u minus au equal to 0 and phi defined in terms of u like this. So if you want to solve the eigenvalue problem for f, this is the eigenvalue problem for f, is it not? Finding all solutions phi. If there is a non-zero solution, lambda will be an eigenvalue. If phi is not a zero solution, there is no non-zero solution, lambda will not be an eigenvalue. So to solve the equation, solve this matrix eigenvalue problem. Okay? If there is a non-zero u as a solution of this equation, then lambda will be an eigenvalue. Then phi defined in terms of u in this manner will be an eigenvector corresponding to the given finite rank operator f. So, and all such eigenvalues and all such eigenvectors must be obtained in this manner, because whenever you have an eigenvalue and eigenvector, this equation has to be satisfied. That is why this if and only if statement is important. Okay, now I have glossed over a small point which I want to come back and so on. In saying all means if u is equal to non-zero, why will I know that phi is not 0? Or if phi is not 0, why will I know u is not 0? That part is not covered. That I want to tell you in the proof. Further, if u is equal to 0, that means all the uj's are 0, then clearly phi is 0. Why? If all the uj's are 0, phi is 0. Is it not? Phi is defined in terms of u1, u2, um. If u is the 0 vector, then u1, u2, um are all 0. Therefore, phi will be 0. Conversely, if phi is equal to 0, then what is u? U is defined in terms of f1 of phi, f2 up to fm of phi. So if phi is 0, f1 is linear, so u will be 0. So phi is 0 if and only if u is equal to 0. That means phi is an eigenvector of phi, because eigenvectors you need to be non-zero, is it not? So phi is non-zero if and only if u is non-zero. Both ways, if and only. That's why the eigenvalue problem for a finite rank operator can be completely solved. That means all solutions, all eigenvectors can be obtained by looking at the matrix eigenvalue problem. This is the main thing, and that is what I wanted to come to. That is, now we have come from infinite dimensional to infinite dimensional. First, we step down from infinite dimensional to finite dimensional. And now we have stepped further down from finite dimensional to finite dimensional. And then we will be able to completely solve this problem. So this I have written something, I think I have only about 5 or 10 minutes. So I will quickly wind up because I have been talking about this a lot. And the whole point of this particular proposition is that no matter what discretization you use, there is a way of creating the matrix A by evaluating the ith functional at the jth element. When that discretization is presented as a finite, discretizations have to be finite. So as is presented in a whichever manner, it is obvious what to take for these functionals and what to take for these elements, and then you have to deal with this matrix. There are certain further comments. There is such a thing as ascent of an eigenvalue, geometric multiplicity of an eigenvalue, algebraic multiplicity, and so on. They are all preserved. So whatever is the ascent, geometric multiplicity, algebraic multiplicity of the finite rank operator, it is the same for matrix A. Let me not go into that. I think I should end my last lecture by giving you some concrete example, because you will say, you are talking in the air. Tell me how to solve a particular problem. So I have taken two simple cases and I will quickly show you how to go about what we have done so far. So the first kernel I have taken e to the power s plus t, and the second kernel I have taken e to the power st. They look very similar, no? In one case it is s plus t, in the other case it is s times t, but they are vastly different. Why? Because the first one I can write e to the s times e to the power t. What does that mean? A function of s times a function of t. So it is already a degenerate kernel, is it not? I don't have to approximate anything. So it's already degenerate. So I can quickly put it in the form as a finite rank operator. Degenerate kernel gives you finite rank operator. So the first problem is going to be trivial. The second problem is not trivial. It is not degenerate. E to the power st. Do you know how to expand e to the power st? 1 plus st plus s square t square divided by factorial 2 and so on. None of this is a product of function of s, product of each term is, but there are infinitely many terms. So you have to truncate them and you have to do some approximation. So in the remaining 2 or 3 minutes, let me quickly show you how to do the first, which is the simplest one, and how to do the second one. So so F1 is the first one, H is the kernel e to the power s plus t, and t has the kernel e to the power st. So F, deliberately I have called it F because it's already finite rank. Okay, so it is a finite rank because this is a function of t into function of s. Maybe I should write the other way. All right, and therefore it's a 1 by 1 matrix. Evaluate the first functional at the first vector. You get e to the power 2t, and it's a 1 by 1 matrix. What is there to do? Nothing to be done. For the second one though, you have to be careful. Expand e to the power st as a power series. And you know that this power series converges to the power to the function e to the power st. So you truncate this power series, j goes from 1 to n. That will give you a degenerate kernel. How will it give you? Because this is a function of s, function of t. And therefore you can use, so here is the degenerate kernel. J goes from 1 to n, e to the power j, s to the power j, t to the power j. And these degenerate kernels converge to the kernel. Why? Because the series converges uniformly. So the degenerate kernel method is what we have written down already here. And you know now what are the functionals going to be, because I have already talked about this while considering degenerate kernels. So the elements are s to the power j factorial j, and functionals are integrals t to the power j. And you formulate a matrix. The matrix for the nth stage, the matrix will come out to be this. You solve this the approximate solutions of the operator equation for T, which is an infinite dimensional operator defined on the infinite dimensional space, will be obtained by matrix eigenvalue problem. The size of the matrix is n plus 1 cross n plus 1. Why? Because I am going from 0 to n, is it not? Wherever I truncate it at 0, no? The series for e to the power s, I started with 0 and I truncated it to n. So there are n plus 1 functionals and n plus 1 equations. So you solve this, you form this matrix an, n plus 1 by n plus 1. And then coming back to what we did in the first lecture, you have Gauss elimination, you have QR method. If you want to solve eigenvalue problem, use the QR method. If you want to solve the operator equation, use Gaussian elimination. So these two examples will show you exactly how you use the methodology that we have created. Now I shall end my lecture by giving you some references which I have referred to sometimes during those 4 lectures. The first one is a book by Mario Alves and Alain Largillet along with me. We wrote it in 2001. It is called Spectral Computations for Bounded Operators. How do you like the title? We were searching for an appropriate title, and our book involved a lot of functional analysis, and also it involved computations. So we wanted to bring both the aspects in our title. So this bounded operator part says, there is functional analysis. Otherwise, why will bounded operators occur? And I wanted to say it is not just functional analysis, it is numerical functional analysis. That is, we are involved with computations. So spectral computation. Anyway, that is our book written in 2001. Then the second is book by Ancelone that I referred to in the first lecture, and I think Ludhi Shah wanted. So I have just added this reference to it in the 15 minutes I was given a break for. So this is the collectively compact operator approximation theory, written in 1971, a seminal book. It created a lot of work in theoretical approximation theory, operator approximation theory. So it's a very important book. Of course, there are now many books based on this. Our book also uses some ideas from this book and so on. Then this is the paper written by Lalita Deshpande and myself in 1990, which covers this big proposition I told you, how to go from a finite rank operator to a matrix in all situations, as far as the operator equations go, as far as the eigenvalue problems go. Then the next one is the paper by Rekha Kulkarni. I told you she came up with a modified projection method, and it is super convergent. You know what is super convergent? Convergent means it approximates well and so on. Super convergent means it converges unexpectedly fast. So you say that the approximation will be of order 1 by n squared. No, it is 1 by n raised to 4. So that is called super convergent. And she has done much work after that also. But this was the first time she introduced it. And this last one is a book written by me. I'm trying to advertise this book, you may say, but there is a reason for it. Many people in India use my book on functional analysis, which I wrote in 1980. But 36 years later, I have written a small book. It is called Linear Functional Analysis for Scientists and Engineers. It is published by Springer, and that is the reason it is not available in a cheap edition. And therefore, it has not found its way in many courses and so on. But those who have seen my first book in functional analysis will definitely appreciate this, because it is much shorter. The first book is 650 pages. It is formidable, no? And that book has almost everything you want. This book is only 250 pages. And all the complicated examples I have removed. So it is very simple. That is why I said for scientists and engineers. So they should be able to access it. But unfortunately, putting this in the title has worked adversely for this, because mathematicians think, oh, this must not be for us, it is for scientists and engineers. No, it is for all mathematicians also, except that it is simple. And more importantly, the solves 160 problems in functional analysis. These are some of the problems that in my original book, people have been asking me, is there a solution manual and so on. There is no solution manual, but in this book, you will find 160 problems solved. So this is my small advertisement. And the last one is the paper by Robert Whitley, who really suggested how to go about finite rank methods to matrices. He did more than that. He also talked about the stability of these methods. Remember, in the very first lecture, I said, you are reducing to finite dimensional matrices and so on. But then there are important questions about conditioning of the matrix, about the stability and so on. So he also considers this stability. We have also when we did work beyond what Whitley did, we have also talked about the stability of finite rank methods and so on. So that's the end. I think I took 5 extra minutes, but I enjoyed coming here. Well, I had not gone anywhere. I'm in my house only, but presenting whatever I know to the extent I can present it to you. So thank you for attending, and I give not the floor, but give the mic. There is no mic also. Give the whatever charge to Shrimai now. So Shrimai, please take over.
Very much, sir. Thank you very much for all the effort and all the dedication with which you have obviously prepared the lectures and given us so many thoughtful insights all throughout the lectures on things that are not in the slides, but beyond them also. You've taken us on this wonderful journey of this approximations of operator equations and eigenvalue problems. And there are many comments coming up in the chat. So most of them are about how much people have enjoyed your lectures. I believe there are some questions also, and I can see that Riddhi has typed a few of them. I can ask Riddhi to please unmute herself and ask the questions.
Sorry, yeah. Thank you, Professor Limaye. It was really wonderful. I just don't remember that. I think you were away when I was a student in 84 to 86.
Yes.
So I really missed a good opportunity to learn from you, but it's never too late, I guess. I used quite a bit of spectral theory and operator theory for my earlier work on probabilities on groups, and also some property T and representation theory. I use that. So yeah, so it's wonderful. I just had again a somewhat simple question. So you are restricting n to means 1 to n, like finite rank n. But in practice, would you take some other subsequence, like say like n square or something which converge faster?
Sure. That's why I used, when I finally did the matrix part, I used the index m. And m can be n squared, it can be n plus 1, it can be 2n, whatever. So
yes. So
any finite number. So
okay. And
for example, this Rekha's method, that is modified projection method, will use double the data. It will use 2n. If projection method uses n functionals and n vectors, this modified projection method will use 2n functionals and 2n methods, because then you are capturing more data. So you have to do a lot of work. So instead of solving a matrix eigenvalue problem of n cross n, you will have to solve 2n cross 2n. But there are dividends, because the convergence will be not like 1 by n, it will be 1 by n squared. So
yeah, so
any
that's why.
number n, any number n, yes.
Okay. Just one quick question. So, I mean, these things you do, like, for separable space, for certain, but in general, you may have a difficult thing, and then you have to devise your own way to go about it and
That is
find
true.
finite rank operators. It's not always restriction, right? So
Yes, yes. When you have non-separable situation, or where you cannot have Chowder basis, or you cannot have orthogonal, that is orthonormal basis, which is countable, then truncating, etc., is pointless. I mean,
can you take a sequence of other finite rank operators which commute or something? I don't know exactly what, but so one has to find one's own way.
I know it will
Yeah.
depend on the particular situation.
Right.
Probably, I have not seen any general theory which will address. I
Or
suppose there
for
are many special cases, then one can think about a theory, no? First of all,
yeah, general theory for a specific space, except I
yes.
mean, okay. Thank you very much. It was a pleasure to be here and listen to you. Thank you once again.
What happened to your piano class?
Yeah, that was yesterday. So I attended your talk in the night. So
Okay.
yeah, last talk, second talk I attended in the night, and now I am also learning how to present stuff from you. So communication is a big thing. So yeah.
Actually, Riddhi, let me tell you, I feel handicapped because I cannot write on the. So there are ways now of writing as you talk, no?
Yeah, yeah.
It becomes a little slow, but it's better to be slow, no, rather than going on bombarding people. So sometime I had to get the facility of doing. Neela was telling me something, but I said I don't want to risk.
Next time, I'm sure you are capable. It's just it took me many months to learn that, but yeah, now I do a little bit better.
Yeah, one has to be practicing. Yeah. Okay.
Thanks.
So I don't see any direct questions as such, only comments apart from these questions. A lot of thank you messages for you, sir, and appreciation of your very informative lectures. And yeah, so are there any questions on the YouTube? I don't see any.
And there is no question in YouTube.
No, there are no questions on YouTube. Okay.
And there is a comment from Ajit Iqbal Singh, ma'am.
Yeah, there are some comments from ma'am. So I will go to that. But I was just looking at the questions first of all. There don't seem to be any queries. Sir, if I might be allowed, I want to quickly ask you something myself.
Okay.
Yeah. So this thing that you have presented in the last lecture for how to go from the finite rank situation to the matrix case, how to convert that to matrix case.
Yes.
So apparently, it does not work if the scalar involved is 0.
Yes. And you know that because
yeah.
0 is always a eigenvalue of a finite rank operator if
Yes.
the domain is infinite dimensional. So for 0, it will not work because for a matrix, 0 is no different. But for a finite rank operator, 0 will be separate because you are dividing by z throughout. Remember that? So it will not. That is correct. For 0, it will not work. But one is hardly interested in 0 as such. No, as an eigenvalue.
Yes.
Okay.
Yeah. So I think there are a number of comments by Ajit Iqbal ma'am, and if she would like to unmute herself and speak up.
Hello. It was
Hello.
a wonderful lecture, Balmohan. I appreciated it very much. And I found your last book very interesting. And your first books are followed as textbooks all over India and elsewhere too. So please make sure that that is approachable to people. That is one thing. And second is, you kept saying that you have to get best definition and best result. So I wrote in jest that good has to be there, then better, and then only best comes. So you can go back and forth from good definition to better result to better definition to better result, and
Okay.
then only you arrive at the best. You do not dream of the best definition or result. You
Okay.
have to work hard towards it, and
Yeah.
that is what I would like the students to follow. They
Yeah.
shouldn't think that best will come in a dream. It
That's
comes
true.
on paper and pen
Yeah.
or keyboard and laptop. It
True. True.
doesn't come from the head like that.
Yeah. Yeah.
It is a yes.
It has to be
And
progressively better and better and better. Yes.
yes. And a wonderful lecture. You explained everything so well, and you put things in a very simple way for students to get encouraged to learn things from you more so. Thank
Ajit,
you.
my question is, are there enough people who want to learn? I
Yes,
find day by day, smaller and smaller number of people who want to learn. That is the sorry state of affairs, but we can't help it. By the way,
that is just fine. If we can train a small number of good people, then they
yes,
will take care of the next generation.
I
Thank
know,
you.
I know. So those of you are listening, and those who have heard Ajit, Ajit Iqbal Singh, we used to call her Ajit Chilana earlier, before her marriage. So we attended many seminars and lectures together. And I will, if you have heard Ajit, you will have noted even now. But in her younger days, she used to be so fast by lecturing. When she will start her presentation or lecture, I will say to my friends who are sitting next to me, "Here comes the Punjab mail." She will remember it. Okay, that's all my comment.
So does anyone else have any comments to make? And you can also unmute yourself and say something if you wish to say.
I would just like to thank Professor Limaye. So, in the last couple of years, especially after the COVID has started, we have been asking him to lecture for many IWM events, especially the young women programs, a couple of times, and this mini course. And he has been always so forthcoming, and he never had said a no, in spite of I mean, he have other constraints, health constraints and so on, but he never said no. And so I would really like to thank him sincerely for making this. And I would also like to say that the participants always, irrespective of the level, enjoy his lectures. So we had something with, as young as BSc second year students. We started with them, and then we had the next year, when they had gone to MSc, those kind of students. And this time it is slightly for PhD students or in that level. And irrespective of the levels, the lectures have been superb. So thank you, Professor Limaye.
Thank you. It's my pleasure.
So does anyone else have any other comment to make? Okay, so you can always write back to us. I have given the email ID of the event. If you feel like giving further feedback, you can always write there, and we will pass it on to Professor Limaye also. And so I would like to conclude, therefore, by thanking, first of all, Professor Limaye for his lectures, for all the effort that he has put into all this. Sorry, Riddhi, we do not have a feedback form. I can see that you're asking for one. As I already mentioned in my reply to everyone, that you can give us a feedback on the email that we posted. And okay, so sir, you started preparing on this a long time ago. I know this. We are privy to that part of your preparation. So, and that shows how much dedicated you are to all these things all the time. So we have so much to learn from you from these things. So I always start preparing for my talks like 2 weeks before the talk is that I'm supposed to give and so on. But you started so long ago, and the effort always shows up in your lectures always. So it's no wonder that you can keep doing what you do so well. So I think for all of us who are teachers here, at some point or the other, we will go on to be teachers, most of us here, even if we are not. There's so much to learn from that aspect itself. And then your presentation, the way you organize your thoughts and put them across. So there's so much to learn from that as well. Apart from the subject matter, of course, you have given us a glimpse to this very important topic. And thank you very much for it. And you have used mostly elementary tools in analysis and linear algebra for doing this and keeping it accessible, as Nilar so rightly pointed it out. And so that's, I think, again, a lesson for all of us here. That complicated things can be made simple and accessible to a very wide audience by presenting and preparing oneself in a right way. Thank you very much again, sir, and we wish you all the best for all your endeavors. You are always busy, we know, with many things lined up, and we hope that we will have you in our midst in future IWM programs, and you will continue to encourage and support us in all our endeavors.
You are most welcome, Srimagi. Okay.
So that's it then, sir. If you have any more final words, then...
No. I said enough.
Yeah. Thank you, sir. Thank you very much.
Okay,
thanks
bye.
Once again to the entire audience.
Yeah.
And thanks to our sponsors, NBHM and the IMU's CWM. And yeah, so that's it for this program.
Okay,
Thank
bye.
you.
Bye, everyone.
Bye.
I'm leaving now. Huh?
Yes, sir. Yes.